Welcome to Chem Talk, where we discuss chemistry. Today we are looking at atomic structure, the building blocks of matter. So our mission for this deep dive, we want to cut through maybe some of the confusing textbook stuff and get right to the heart of the atom.
Yeah, figure out what it's made of, how we count those parts.
Exactly. And, the big goal is for you listening to walk away really knowing what makes, say, nitrogen. Well, nitrogen and not oxygen.
Yeah.
What's that fundamental difference?
And it all starts with the atom itself, which is like the smallest possible piece of something that's something.
Like the smallest bit of gold that's still, gold.
Precisely. Or like maybe Lego bricks, the individual bricks that make up everything else. That's the atom.
Okay, but here's the first, mind-bending thing. Atoms aren't tiny solid balls.
Not at all. They're actually almost entirely empty space. It's pretty counterintuitive.
Empty space. How does that work? What is there then?
Well, right in the middle, you've got this incredibly dense core. That's the nucleus.
The nucleus, okay.
And pretty much all the atom's weight, its mass, is packed into that tiny, tiny spot.
Right, I remember the analogy for this, the stadium one.
Oh, yeah, the stadium analogy is perfect.
Got it.
Imagine an entire football stadium. The whole thing represents the atom.
Okay, huge space.
And the nucleus. It's like a single marble placed right on the center spot, the 50-yard line.
A marble in a whole stadium. That's, wow.
And the electrons are even smaller, like little gnats flying way up in the stands. The rest is just emptiness.
So wait, if I'm touching this desk, and the desk is atoms, and atoms are empty, why does it feel solid? Why doesn't my hand go right through?
That's the other weird part. It's not about solid stuff hitting solid stuff. It's about forces.
Forces?
Yeah, the electrons in the atoms of your hand are repelling the electrons in the atoms of the desk. It's like invisible force fields pushing against each other really, really strongly. You feel the force, not the stuff.
That actually changes how you think about that. Well, everything. Okay, so
Yep.
back to that marble, the nucleus,
Mm-hmm.
and the gnats, the electrons.
Right. Inside the nucleus and buzzing around it, we have the three main subatomic particles you need to know.
The ones that decide everything.
Pretty much. They are protons, neutrons, and electrons.
Okay, let's break those down. Protons first.
Protons, they live inside the nucleus, and they have a positive electrical charge. We usually write it as P plus rho.
Positive charge in the nucleus. And these are the important ones for identity, right?
Absolutely critical. The number of protons is what defines the element. It's non-negotiable.
Like a unique fingerprint or maybe a barcode.
Exactly like a barcode. Every single atom in the universe with, say, 6 protons is carbon. Always. If it had 7 protons, it'd be nitrogen. Change the protons, you change the element.
So that number, the proton count, that's the atomic number Z that we see on the periodic table.
That's it. Z equals the number of protons. Carbon is Z6 because it has 6 protons. Simple as that.
Okay, got the identity part. What about the next particle in the nucleus? Neutrons.
Right, neutrons. They also live in the nucleus, shoulder to shoulder with the protons, but crucially, they have no electrical charge. They're neutral. Hence the name, neutron, N0.
Okay, no charge. But hang on. If the nucleus has all these positive protons packed together and positive charges repel each other, shouldn't they just, push each other apart violently?
That is an excellent question. And you're right, they should. The electromagnetic repulsion is huge in such a tiny space.
So why doesn't the nucleus just explode?
That's where the neutrons come in. They act like padding or maybe peacekeepers in a crowd.
Peacekeepers.
Yeah, they provide some spacing between the protons. They don't have a charge, so they don't add to the repulsion, but they help hold things together. They add bulk that allows this other force, the strong nuclear force, to overcome the repulsion and bind the nucleus.
So they're like nuclear glue, stabilizing everything.
That's a great way to put it, nuclear glue. Especially important in bigger atoms with lots of protons repelling each other.
Wow. Okay, protons for identity, neutrons for stability. Without the third player, electrons.
Electrons. These are the tiny negatively charged particles, symbol E, and they don't live in the nucleus.
Right, they're the gnats in the stadium analogy, orbiting far away.
Exactly. They exist in specific energy levels or shells around the nucleus in that vast empty space.
And they're super light, right, like almost no mass compared to protons and neutrons.
Negligible mass. We basically ignore their weight when we're talking about how heavy an atom is. It takes almost 2,000 electrons to equal the mass of just one proton or neutron.
But they must be important for something.
Oh, absolutely. Their negative charge is key. In a neutral atom one with no overall charge, the number of negatively charged electrons perfectly balances the number of positively charged protons.
Ah, charge balance. So if carbon has 6 protons, positive charges?
A neutral carbon atom must have 6 electrons, negative charges, to balance it out. Plus 6 and minus 6 equals 0 overall charge.
Okay, that makes sense. Identity, stability, charge balance. Got the players. Now, how do we use this with the periodic table numbers? We already covered atomic number Z is protons.
Right. The other key number is the mass number, which we symbolize with A.
Mass number A. Okay, what's that counting?
It's simply the total count of particles in the nucleus. And since the nucleus only contains protons and neutrons...
So mass number A is just protons plus neutrons.
Sure.
A equal P plus N.
Exactly. We ignore the electrons because they're too light to matter for the mass number.
So Z tells you the element, A tells you the weight of the nucleus.
Pretty much. And you can use these two numbers to figure out everything. Let's take an example. Boron.
Okay, boron. Looking it up. Atomic number Z is 5.
Right. So you immediately know boron has 5 protons. Now, boron atoms can have different numbers of neutrons. Those are called isotopes. But let's say we're talking about a specific isotope, boron 11. That 11 is its mass number A.
So A11, and we know Z5, which means P5. To find the neutrons, we just subtract.
You got it. A P plus N. So N equal AP.
N equals 11.5. That's 6 neutrons.
Perfect. That specific boron atom, boron 11, has 5 protons and 6 neutrons. See how A is a nice whole number? Because you're just counting particles.
That seems straightforward enough. Okay, so we know the counts. How do we, picture this? You mentioned shells for the electrons. Is there a simple model?
Yeah, the easiest one to start with is the Bohr model. Now, disclaimer. It's not really how electrons behave. They're more like probability clouds, but it's fantastic for visualizing basic structure and energy levels.
Okay, so a simplified picture. How does it work?
You start with the nucleus in the center. Just draw a circle.
Okay, circle for the nucleus.
And inside, you label the number of protons, P plus, and neutrons you've figured out.
Got it. P plus and N0 in the middle.
Then you draw concentric circles around the nucleus. These are the electron shells or energy levels.
Like orbits.
Kind of like orbits, yeah. And then you place the electrons on these shells, but there are rules.
Rules. Okay.
Electrons always fill the lowest energy shells first, the ones closest to the nucleus. And each shell has a maximum capacity.
What's the capacity?
The first shell, the innermost one, can only hold a maximum of 2 electrons. That's it.
Only 2. Okay.
Once that's full, any more electrons have to go into the second shell. The second shell can hold up to 8 electrons.
2 on the first, 8 on the second. Got it. Let's try an example. Lithium. The source mentioned lithium.
Good one. Lithium, find its atomic number Z.
Lithium, Z is 3, so 3 protons. And for a neutral atom, 3 electrons too.
Right, and let's use the common version, lithium DAS of 7. So its mass number A is 7.
Okay, A7P3. So neutrons. 8pp for 7, 3 equals 4 neutrons.
Perfect. So draw your nucleus inside.
3p plus and 4 sub.
Excellent. Now the electrons. We have 3 electrons to place. Where did the first ones go?
Okay, first shell. It can hold 2 max. So put 2 electrons there.
Right. Shell 1 is now full, but we have 1 more electron left over.
So that last one has to go onto the next shell, the second shell.
Exactly. So the Bohr model for lithium-7 shows 3p plus and 4 ended in the nucleus, 2 electrons on the first shell, and 1 electron all by itself on the second shell.
And that single electron on the outer shell.
Yeah.
That's important, isn't it?
That's everything, chemically speaking. That outermost shell is called the valence shell, and that lone electron defines lithium's personality. It's unstable like that. Lithium really wants to get rid of that 1 electron to have a full outer shell underneath.
Which makes it reactive.
Highly reactive. That's why lithium is an alkali metal. The Bohr model, even though it's simple, shows you why it behaves that way. It points right to the valence electron.
Okay, that actually ties a lot together. So quick recap then. The nucleus, tiny, dense, holds the mass, protons plus neutrons, and the identity, protons.
Right. Protons P plus give the atomic number Z and define the element. Neutrons N0 add mass and stabilize the nucleus.
And the electrons E, way out in the shells, are super light, negatively charged.
They balance the proton charge in a neutral atom, and their arrangement in those shells, especially the outermost one, dictates all of chemical bonding and reactions.
So if you remember, Z is protons, and A is protons plus neutrons. You basically got the atomic toolkit.
You really do. That's the foundation. Now, here's something to chew on, maybe look into after this.
Okay.
We said the mass number A is a whole number, right? Counting protons and neutrons. But if you look really closely at a periodic table, the number at the bottom, the atomic mass, It's usually a decimal. Lithium is like 6.941.
Huh. Yeah, it is. But you can't have 0.941 of a neutron,
Yeah.
so what gives?
Exactly.
Yeah.
If you can't have fractions of particles, why is the average mass listed as a decimal?
Hmm.
That's your next step, thinking about isotopes, different versions of elements with different neutron counts, and how we average their masses based on how common they are in nature.
Yeah, isotopes and averages. Okay, something to investigate further.
Yeah.
Cool. Well, this has been incredibly clarifying, and a huge thank you to the geeky gamer science teacher for creating this deep dive.